Last week I gave a presentation at IPMU 2024 in Lisbon, which is the International Conference on Information Processes and Management of Uncertainty in Knowledge-Based Systems. And I thought I would record and use the same slides to sort of put a video on YouTube with the same content. The presentation shows the status of the ideas that we have in the use of non-additive measures in quantum mechanics, and this is the project that has been sponsored by the John Templeton Foundation. And I went to that conference mainly to talk and find people that are expert in the mathematical techniques that are used in a completely different settings, so that they could give me pointers and I can understand how these techniques are used. So, first that I did was give an overall overview of our project, and for those things this channel should probably already know that my project is called Assumptions of Physics, and the aim is to identify a handful of physical starting points from which the basic laws can be rigorously derived. So this is the idea that in modern physics we are just given a physical theory with a mathematical structure, and it's not really clear where that mathematical structure comes from, and the idea is that we want to tease out a certain element assumptions or principles from which we can actually derive the mathematics, so that we know what the physical theory is describing. And we have these two techniques. One is called reverse physics, that starts from the physical theory, that starts from the math, and tries to get these equivalent principles. And then we realize this is not sufficient, because if you use any mathematical structure and you don't know exactly what the mathematical structure is captured physically, then even if you know what the higher level mathematical structure are, you really don't have the full pictures. So if you don't know what are the assumptions that go into using the real numbers in physics, well, you still have holes underneath and you don't know. So we have this other approach called physical mathematics that really starts from scratch and layers each axiom and definition with a physical justification, so that you know exactly what the symbols are supposed to represent, and therefore everything in the mathematical structure now is physically meaningful, and that's why it's physical mathematics, it's physically meaningful mathematics. So the reason why I went to the conference, of course, is not to discuss physics, but is because quantum mechanics violate classical probability, and this is something that we have known for more than a century now. And classical probability is really additive measure theory. It's an additive measure with that is bounded to 1 on the full space. And quantum mechanics, therefore, can be seen to violate additive measure theory. And so the question is, can we use non-additive measure theory for a physically meaningful generalization? And what tools should we or should not we use to achieve this goal? Okay, so this is basically the purpose of the talk. So let's first look at what the problem is. And again, if you know quantum mechanics, probably these things you've already seen, but if you come from the fuzzy community and imprecise probability and so on, you might not know, and that's why I had this slide. So one of the first type of things that you can use to see that the quantum mechanics violate classical probability and classical measure theory are the Bell type inequalities. So here, for example, I have 3 events, A, B, and C, which in physics could represent I have spin up, I have spin right, or I have a spin upright. And in the context of classical probability theory, if I have the event that it's in the intersection of the two, so it's A and B, then the probability of having this event is less than the probability of having A and C, plus the probability of having A and not C. And you can see that this has to be greater to this, because this set plus this set is strictly greater than this set, and therefore the probability can only be equal or the same. And this inequality is something that you can violate in quantum mechanics. You can sort of construct some things where these propositions don't satisfy. The probability for this proposition wouldn't satisfy exactly the Bell-type inequality. And everything that you can do similar things with expectation values. So suppose that we have 4 random variables, each of them with that they can only get 2 values, -1 or +1. So this random value can only get these 2 values. And then we have that the big A and small a are very, very strictly correlated in the sense that either their difference is 0 or their sum is 0. So you have either one or the other case. And if you do the calculation of this horrible expression here in terms of classical probability, you will find that this has to be less or equal to 2. And again, in quantum mechanics, you can find variables such that this expression is equal to 2 square root of 2. And so this again tells you that classical probability theory and therefore standard measure theory does not work in quantum mechanics, and therefore you need to find something else. Now there is something else that is used and is actually very useful to use in quantum mechanics, which are the quasi-probability distribution, the so-called Wigner functions. There are a couple of other transformed the same way. The idea is that you can take your states and sort of re-express them as this distribution over position and momentum, and this is useful because you can recover the marginal distribution, and you can also recover expectation value by doing the integrals as you would do if, with a classical probability distribution. However, the problem is that this function can be negative, and it's not really clear what it means to have a negative probability. And it's sort of, on the measure theory side, it doesn't quite work exactly like you would expect, in the sense that when you do probability with measures, you first define the measures and then you define the probability density. And here instead you define the probability density first, and it's also not clear exactly what is the space of the allowed density. So if you have a classical space, any density distribution that integrates to 1 positive, or where all the elements are positive, then integrates to 1, that's a valid probability measure. And here it's not clear which types of density are in, are out. And so it's, from a physical perspective, it's useful for calculation, but I don't think it's really useful to understand how things work. And then again, the problem is that formally this works differently than classical probability, and we really want to have objects that formally works the same in classical mechanics and quantum mechanics, that have the same physical justification, so that we can sort of create a state, an abstract space of states and processes. And so this really does not work. And so the question then is whether we can find a generalization of probability theory that works in the same way in both classical and quantum mechanics. That is, the space, the sample space in the probability theory is the respective state space, which is something else that the Wigner function does not work like that. The position and momentum, the points of position and momentum are not really quantum states. So you're putting a probability distribution, a quasi-probability distribution, on a space that is not really the state space of quantum mechanics. Then we want the probability defined as a set function on the sample space, exactly the same as everything else, and the expectation recovered as some sort of integral of some function of the sample space. And so the question is, what set function for probability, how that work, what integral for the expectation, and what derivative to get the probability density. So these are the questions, and we have a proposal. We have a set of definitions that we think that they work, and that's what we are going to present right now. So the key insight here is that we can look at the probability as the biggest coefficient when we are mixing measures, when we are doing convex combination. What do I mean by that? Well, suppose that we have a probability measure. A probability measure is something that you give a set and it gives you a number. So, for example, if this is our probability distribution and we take the set U, the probability of U would be the integral underneath this set. So if you had another set here, it would be the integral of this set. This is kind of backwards because, again, in measure theory, you're first given the measure and then you go and calculate the integral, but sort of to give you an idea. And so what you can do with conditional probability is say that the probability of A is equal to the probability of A given U times the probability of U, plus the probability of A given UC times the probability of having UC. And so this is a measure, like it's something that takes sets and gives you a number. This is also a measure, but it's restricted to U. It's a measure that it's only on U and it's 0 everywhere else. This is a number, this is another measure, and this is another number. So what you're doing here is really have a convex combination of measures. You have two measures, you have two numbers that sum to 1, and you construct a measure as a convex combination. And so what happens here that is interesting to me is that if you take any measure restricted to U, right, you can always write a linear combination, a convex combination with that measure, assuming that everything is non-zero. You can always write this as a convex combination, but the weight that you're going to put on this distribution is going to be less than the probability of U. And so if you take all the possible convex combinations from anything that has support on U plus anything else that gives you the original probability measure, you find that this probability of U is the maximum. So if you take this E as the convex space of probability measure and EU the convex subspace of E with support U, then you find that if you take a measure from E, then the measure in U is you can find it as finding all the possible convex combination of all the elements in EU plus elements outside. You find all the possible weights that you put here, and you take the supremum, and that supremum is going to be the mu U. And so this is going to be a property that measures have. And now what we're going to have, what we're going to do is start with convex combination and define measures with this property. So instead of having measures that have this property on convex combination, we start with a convex combination and we find the measure by defining by using this property. So the general structure for a space of ensembles, this is basically what we want to have. The idea is that ensembles are the basic element of a physical theory, because whenever we are going to perform measurement and we want to test a certain physical theory, we need to gather statistics. We need to make sure that things are repeatable and that we always get the same statistics and so on. And so the idea really at a conceptual level is that physical laws always are giving us a relationship between ensembles and ensembles. They are always, whenever I have this type of preparation procedure and I perform this type of measurement, I get this statistics, because these are the things that we can produce in the lab and prepare. And so the idea is to create a fundamental definition for a physical theory based on the notion of ensembles. And ensembles have these two things that we always need to be able to do with ensembles. One is we need to be able to mix them, because if we have a preparation procedure that you can imagine the preparation procedure as spitting out sort of different instances of preparation, and the ensemble being the collection of all these preparation from that you can ever do with the preparation procedure. And then you have another preparation procedure. You can always make a third preparation procedure by selecting one of the two with a given probability. I take 30% of the time this and 70% of the time the other. So when you put them together, you can always create a new ensemble from ensemble. From two preparations, you can always create another preparation. And this is given by a convex combination. So we have an ensemble, another ensemble. We select the probability from which you take one or the other, and you would get always a new thing. And this is going to form what is called a convex structure on the space of ensembles. The other thing that we always need to have defined in physics is an entropy, because this ensemble sort of has to be a stable preparation, right? If you take a set of outputs now and a set of output by somebody else somewhere else at another time, the statistics has to be the same, right? So that there has to be some sort of equilibrium in this sense, that the ensemble is always equal to itself. And if you, by thermodynamics, we need to have an entropy defined. This is the thermodynamic entropy. And the important things to me is that all these things are operational defined, and they are physically either measurable or identifiable. We need to be able to look at an ensemble, do enough measurement to identify, oh, we have this ensemble instead of another ensemble. We can, if we have a mixture, if we know that there are two ensembles that are being mixed, we can actually go and measure the probability that is being used for the mixing. And the entropy itself, the thermodynamic entropy, is also a quantity that it's operation, like we go and measure it. And so this means that the fundamental structure that we're giving is physically well defined. It's connected to experiment. Another thing that is important about the entropy is that it's a concave function of the ensembles. Actually, it's strictly convex. What does that mean is that if you make a convex combination of two ensembles and you compare it, you subtract the average entropy of the two ensembles by themselves, then this difference can only be non-negative. That is, if you take two things and you mix them, the entropy always has to go up or stays the same. You can't decrease entropy by mixing things. And this makes sense if you imagine that entropy is a measure of the variability of the elements of the ensembles, if it's a measure of uncertainty, and so on. But the entropy is strictly convex, meaning that the only case when you're mixing two things and the entropy doesn't go up is when the two elements are actually the same elements. So the no increase is equality, so the entropy knows about the equality. On the other side, if you take two ensembles and you increase and you mix them, you have a maximum increase. You can't take two ensembles and increase the entropy arbitrarily high, and you get the maximum increase when you have two distributions that have no overlap. And at that point, the entropy that is being added is really the information about the choice of which distribution you got, and therefore the maximum increase is given by the Shannon entropy. And also, this case of no overlap mathematically is the orthogonality in the space of the distribution, and this is true for both classical mechanics and quantum mechanics. And so what happens is that really the entropy knows about the geometric structure of the full space of ensemble. And this is true for both classical and quantum mechanics. If you give me classical or quantum mechanics and you tell me all the space of the ensembles and their entropies, then you can recover the geometry of the space. And if you give me the geometry, well, geometry is the thing that you give me to actually go and be able to compute all the entropy. So once you give me the entropy, you have completely fixed the geometry, and this is how it works. This expression here is actually not something that I made up. It's something that exists both in classical mechanics and in quantum mechanics, or classical information theory and quantum information theory. It's the Jensen-Shannon divergence, and it's a semi-metric, meaning that it satisfies all the axioms of the metric except that it's except for the triangle inequality. It actually turns out that it's the square of the metric. But then if you make the infinitesimal version of this, what you find is that you can recover the Fisher information metric for both classical mechanics and quantum mechanics. So the point is that these are very nice definitions that map directly, very closely to things that we already have in classical mechanics, quantum mechanics, information theory, and allows you to make a lot of links. Okay, so we have this space of ensembles. So how do we get to this sort of probability measure that is non-additive? So we take we define the hull, And the hull of a subset of U is a subset of ensembles, is going to be all the possible convex combinations that you make with a probability over U. So you just take a bunch of elements over U, you make all the possible convex combination, and that's the hull. It's the convex set with all the convex combination. And now we define the probability. How do we define the probability? Is we pick an element, and then we say, what is the probability that that element is in this subset? Well, that thing gets defined in this way. You take the hull of U, you make all the convex combination with an element inside U and something else. And so this is going to be the set of, the fraction of that ensemble that can be seen as a convex combination of elements of U. And from all this possible P, you get the biggest one. And so the probability is really the biggest coefficient reachable by a mixture of elements of U. It's basically the part of E that can be seen as being a mixture of U. And this is going to be a set function because this takes a set of elements in U. And so it's a function that takes a set and gives us a real number. The function is non-negative and unit-bounded because we're taking the supremum between the interval of 0 and 1, so it can only be between 0 and 1. It's monotone because if we increase the set, the hull can only increase, so the set of all possible P can only increase, and therefore the supremum can only go higher. So it's very monotone, very simple to demonstrate. And it's subadditive because what happens is that if you're making a convex combination of element of U and V, well, those are going to be convex combination of element inside U and V, and so the biggest coefficient for U is going to be given by this, the biggest coefficient that you can have in V is going to be given by this, and therefore the coefficient that you give to a linear combination of those two things can only be to those two things, or less in case that actually part of U is in V and part of the V is in U. And then what I'm not going to show you here, but the idea is that if you can take the space and decompose it in orthogonal subspaces, then you recover the additivity. So this can always be done in classical mechanics, so you will find that this measure is additive and corresponds to the standard probability. And you can also do it in quantum mechanics on the space of the outputs of a measurement, the spectra of a Hermitian operator. Also there you can show that the space for each eigenvalue is orthogonal, and therefore you can make this decomposition, and therefore you recover that the probability is additive there, and you can actually reinterpret it as you would do in the standard probability. So now let's give you an example of how this actually works. The simplest classical case would be we have two states and we get the simplex, so that is the space of all possible probability distribution. It's either the two-dimensional simplex or one-dimensional simplex, depending on how we define the dimensionality. But the idea is that this is, one possible state, the other one is the other possible states, and then you have here all the possible probability distribution that are just given by a single number, right? So here you would have 100% in 0, and here you would have 100% in 1. And so if you characterize this each point in the convex mixture by this parameter P, you have the measure over nothing is 0, the measure over both points is 1, the measure on 0 is P, and the measure over 1 is 1 minus P. So you have a standard probability distribution. So now how does that work in quantum mechanics? Well, we are going to take the two-state system, and the two-state system, the space of convex combinations of all the pure states is given by the block ball. And so here we have the state 0 and the state 1, and like in classical mechanics, these are the mixture of 0 and 1. But in classical mechanics, you not only have the mixture, but you also have the superposition. And the superposition is just a fancy way to express the fact that you have all these other points on the surface, and this corresponds to the pure state. And any point in the middle becomes a possible mixed state, a possible density matrix. And so Any density matrix can be parameterized by three numbers. One, the radius from 0 to 1, then the azimuthal angle, and the longitudinal angle. Okay, so now if we pick an E that is parameterized by these numbers, we can go and calculate that measure, and we're going to do this for three simple cases. If we have the empty set, then of course the probability is 0. That's the biggest component that we can get. If we have the full space, of course, is 1, because we can, with a convex combination of the points, we can always get to the actual ensemble. And if we instead take any point on the surface, we get this expression that is going to be depending on the radius where you are and the difference in azimuthal angle between E and theta. As two simple examples, if the target ensemble is a point on the surface, then either the 2 points are the same and you have probability 1 to have that particular point, or you have probability 0 to get to the other point. So again, this makes sense. It would be like a delta distribution on a single point. Or if you take the point in the middle, this point is equidistant between every other pure state, and therefore you're going to get that the probability of having any pure state, given that you are that you have the maximal mixed state, that you have the origin, is 1/2, right? So this is the case where you have all the probability concentrated in one point and 0 on the other, and this is the probability where you have 1/2 of that you have a uniform distribution. But now the uniform distribution is over the whole sphere, right? And so this is where you can see that it's not additive, because if you sum 1/2 over the whole sphere, of course you get a lot more than 1/2, you get infinity. Okay, so this is how you construct that quantity, how you calculate the measure. And this E is our target ensemble, the ensembles that we have. A is the point which we are asking what is the probability of having A given that we have E. And the way that you do it is that you take A and E, you make a line, and then you have the other intersection B. Therefore, E can be seen as a mixture of A and B, and the probability of having A is this segment divided by this segment. This is always a little bit confusing when you look at probability as convex combination. The corresponding probability is on the other side, and you can see that if you are here, right, you know, if E is here, you would have 100% probability of having A, and that of course means that this side divided by this side is equal to 1. So you can go and check if you want that this is actually correct. And here I have a small video where I show you exactly the calculation. And the idea is that we have A here, which is the point where we want to calculate the probability, and it's going to be the probability that we have here. And this graph will go from pi to minus pi, and so you're going to see the probability on all the points of the circle. Of course, the probability is going to be symmetric rotating, so I would just do it in the one dimension. We're getting a section of the ball, essentially. And then I will move this E around, and then you will see how the probability works. So, for example, we start by taking E and moving it around on the space of pure state, and then you see that you have a probability that it's 1 or 0, and that 1 sort of moves around depending where you are. And now we're going to take E and move it down, and you can see that the distribution sort of spread out. And if we move it around in a circle, again, you can see this moves around like a wave. And now if we put it at the origin, now that's where you get the probability that it's uniform over the full space. So again, so this definition kind of works, it kind of makes sense. And the idea is to see whether this actually works in a bunch of different ways. So the first reason why this makes sense and what this shows is that the non-additivity of measure, it's really caused by the possible multiple decomposition or by the contextuality in quantum mechanics. In classical probability, you have a single decomposition for pure states. If you take any point here, then there are only two extreme points, and therefore you can only describe it as a single convex combination of the extreme points, and this generalizes to all other cases. Every classical probability is a singly decomposed in terms of the pure states, while in quantum probability you have multiple, in fact infinite decomposition. If you take a point here, this could be the convex combination of these 2 points or of these 2 points. Basically, any line that passes through this is going to intersect the sphere in 2 points, and so that point is going to be a convex combination of those 2 extreme points. The other thing that is interesting here is that we actually have a finite probability on each point of the continuum. So every point here would have a finite probability, and it's not a probability density. It's not something that you integrate in the standard sense. And I want to stress that the degree of additivity is really, really high, because again, if we take the probability of the full set for the maximally mixed state, the point in the middle, you would have that has to be 1, because it has to be 1 for everything. And this has to be less than the sum of the probability for each point on the surface. And the point of the surface, we saw that the probability of getting any point is 1/2. And so this is the sum of 1/2 the cardinality of R. So this is really infinite. It's a big infinity. And so, and again, this makes sense because since we saw that the non-additivity is caused by the multiple decomposition, we have uncountably many decomposition. We have the cardinality of the decomposition is like the cardinality of the continuum, so that's what we have, and so it makes sense. Another thing that we want to define now on these spaces are the idea of random variables. And again, we want to define them on the ensemble first and then recover what happens on the pure states, because that's the structure that is going to be that can be made the same in both classical and quantum mechanics. And the idea is that then any random variable is just a function of an ensemble that gives us a real number. That is linear, meaning that if I have a convex combination of ensemble, then I'm just making the average of the values. And this is because every random variable corresponds to an expectation, and this operator here is really the expectation of the random variable. And if you define things like this, you can recover the standard way of thinking at random variable in classical mechanics. That is, you can, since you do have this linearity, you don't really need to tell me the expectation value for all possible ensembles. You can just give me the value for 1, the value for 0, and then everything else is just the expectation. And so you can find, if you define things like this, is that you can find that f of e is just the expectation, and you recover things that are standard. In quantum mechanics, you can sort of do the same. You can show that if you have something that is a linear functional of the ensembles, you are going to find, for example, for the block ball, is that this is going to be a linear function inside this space. And you are always going to find 2 points that are opposite to each other, such that everything essentially is defined by this gradient. So once you know these 2 points and you know the value that f gets at those 2 points, then you can reconstruct the value everywhere else. And in quantum mechanics, these 2 points become the eigenstates of the Hermitian operator corresponding to the observables, and the 2 values become the eigenstates. And so you do get the same thing that you have in quantum mechanics, but really what we like to write, is that this value of the variable applied to the ensemble is an expectation, and it's some kind of sum or integral of the probability that we have defined before on each point with the function that defined at each point, right? So we would like to be able to express this in the same way as this. Of course, this is not going to be a sum anymore. It's not going to be an integral anymore. We have to find what it is, and the hope is that this would magically correspond to the Choquet integral that is being used in adaptive measure theory. Of course, if that's the case, we don't know yet. If that's the case, then we would basically have complete similarity, because the Choquet integral on a classical measure becomes exactly the Lebesgue integral, so we would really be happy. So is this gonna work? I don't know. That's part of why this is research, and that's part of why I went to that conference, to see if there are people that can help me figure out whether this works or not. Okay, so that was all about probability and expectation value, but there is something else that we use measures in physics, especially in classical mechanics, which is for the count of states. So in classical statistical mechanics, there is a link between entropy and the geometry of the space. It basically tells us that we have a uniform distribution over U, then the Shannon-Gibbs entropy is equal the logarithm of the count of states. And this is also called the fundamental postulate of statistical mechanics. So we see that this measure is linked to the entropy, and we can also see that the if you take the logarithm and bring it on the other side, you would have that the measure is the exponential of the entropy. So this sort of plays an important role in classical mechanics, because it links the entropy to the count of states. Now, in quantum statistical mechanics, you have somewhat of a related expression. If you have a uniform distribution over a set of states and you calculate the von Neumann entropy, this is going to be the logarithm of the dimension of the span of U, so the dimension being the dimension of the Hilbert space that is being used. And you're going to have an equality here if you have a uniform distribution over the whole span, over the whole state. And so the question is, can we find some generalized expression that links the count of states to entropy, such that we can also have a measure of counts of state in quantum mechanics, so that we can, again, have a perfect analogy, a perfect formal analogy, not real analogy, perfect formal equivalence of the two systems, such that we can see those two systems as sort of variation, these two theories, a variation of a bigger theory. So the first thing that one can demonstrate very easily is that the exponential of the entropy is subadditive, meaning that if you have two states and you make a mixture of them, then the exponential entropy of the mixture has to be less or equal to the sum of the exponential entropy, and you get an equality if and only if the two elements are orthogonal to each other, if they maximize the entropy during mixing, and the probability is this, is the exponential entropy of the first divided by the sum of the exponential entropy, right? And this is essentially a very general thing that is valid for classical mechanics, quantum mechanics, and quite frankly, even if you don't know what space it is, as long as we satisfy those axioms for examples, this is always going to be valid. And so the idea is to define a state count given a set of ensemble as the supremum of the exponential entropy of the hull. That is, you take all the possible convex combination, which is the hull, you calculate all the entropy, you calculate the exponential of all those entropies, and then you take the biggest one, you take the supremum. And again, what you can demonstrate is this is a set function, because it takes a set and gives you a number. The number has to be non-negative because it's an exponential of something, and the exponential of something can only be 0 or positive. It is monotone because, again, if you make the set bigger, the hull is going to be bigger, and so you are going to calculate more possible entropy. The set of possible entropy is going to increase, and the supremum can only go up. And so this is a monotone set function, and it's subadditive because we saw that the exponential entropy is subadditive when you're making a convex combination. So if you have two subspaces and do the convex combination, at most you're going to be adding them, and you're going to actually adding them again when the space can be decomposed into orthogonal subspaces. So this, what happens is that this recovers the number of states for discrete classical spaces, it recovers the Liouville measure for continuous classical spaces, and recovers the dimension of the subspace in quantum mechanics. So the point is that this same definition applied generally gives the correct things in all the different cases. So This again, and again, it's very simple to demonstrate these things, so really gives me a warm and fuzzy feeling that I am getting the correct definition. And one of the way that we can see that we need these non-additive measure for this count of states is by, again, looking at the block ball. What's going to happen is that if you have one point, right, one pure state, then the measure for a set of one states is 1, because the entropy for a pure state is 0, so 2 to the 0 is 1. So every point counts as one state, which makes sense. If you have 2 points A and B that are orthogonal in the sense that they are that they belong to orthogonal subspaces, and then we make all the possible convex combination, of course, the things that is going to be have the highest entropy is the point in the middle, which is going to have 1 bit of entropy. 2 to the 1 is equal to 2, which means that the set of A and B can contain or is defined by 2 states, which is good. But then if you take A and C, well, these two are gonna make a maximum convex combination, and the entropy of that is not gonna be 1 because they would have to be here. It's not gonna be 0. It's gonna be a little bit more. Therefore, this entropy here is gonna be greater than 1 and less than 2, and so it's not additive. It's not gonna be 1 plus 1, but it's gonna be less, and it's gonna be sub-additive because we can't make as much as that. And so in quantum mechanics, literally you have 1 plus 1 is equal less than 2, and this is kind of why you make, this makes a little bit, which is sort of the things that it's strange in quantum mechanics, that you have 2 distinct states, but those 2 states are not really 2 states chosen at everything else being equal. So if you have A and C, the way that you prepare A is different than the way that you prepare C. The way that you measure A is different than the way they measure C. And so, yes, there are 2 distinct states, but they're not 2 distinct states that where all the boundary conditions are the same. So they are more than 1 state, but not quite as 2 distinct cases where everything else is equal. And so what is another way that I like to look at this is that ideally, if you wanted a measure for how many states you have, you would like to have these 3 features. First, so that if you take a single case, a singleton, then you have 1 case, so you have 1 state. If you have a finite range, well, a finite range is, on continuous quantities, they carry finite information. Therefore, you would like to have a finite measure on the number of states, and you would like the measure to be additive over disjoint sets. If you have a set of states and a set of states, and there's no state that is sort of together, then you would like the measure to just be the sum. And the problem is that these 3 things are not compatible with each other. So you always have to pick. You can only pick 2, and you have to disregard the third. And what happens is that if you have the sort of the classical discrete case, then you have the first, you have the third, but you don't have the second. The measure over a finite continuous range is going to be infinite. If you are on the continuous classical case, then you have a finite, you have the second, you have the third, but the points are going to be measure 0, and therefore you don't have that 1 point is equal in a single case. And in quantum mechanics, you're going to have the first and the second, but you're going to disregard the third. So that's sort of how it works. And that's about it. So this is sort of the status that we are, and the idea would be to make everything that we have seen work in a consistent theory with the correct thing, and then basically see if we can recover some interesting results from the use of these measures. And as a sort of overview, we've seen that in our project, we're looking for a generalized setting for both classical and quantum mechanics to do states and processes in the same way that it's formally exactly the same. And the setting is this idea of a convex space of ensembles at equilibrium that, since they're at equilibrium, they have an entropy, and then we can mix them, and that's the only thing that we need to require from from the States. And again, the good thing for me is that all those things are operationally well defined, that they are things that we know what they mean experimentally. This generalization requires non-additive measurements to deal with the multiple decomposition, the idea that we have contextuality in quantum mechanics. And non-additive measurements are not typically used in quantum foundations, and that's why I went to this conference in completely different field to actually go and look for advice and discussion and collaboration. So if you are watching this and you're an expert in fuzzy measures and so on, you want to help me out, contact me. And everything that is really good about this approach is that the same generalization connects to other areas of math and physics. Information theory, information geometry can be recovered, as I said, the Fisher information metric, the Jensen-Shannon divergence, all this comes out straightforward from our definition. The idea of functionalizing spectral theory come out when we have this linear operation of ensembles and we have to go and look at the possible values. So we're trying to sort of take spectral theory and readapt to make these things work. And order theory and quantum logics, this is also something that it connects to, because the way that we recover classical probability over measurement is basically very similar to what people did in quantum logic. And this was my for more information slide. The fact that we have these two YouTube channels, which if you are on YouTube probably already know. And yeah, so another thing that I should do is thank Vincent and Susanna, who are the people that I sort of randomly contacted at the beginning of the year to start getting oriented in the world of non-additive measurement. And they actually were very helpful and they were graciously to sort of hear me rambling on things that were a lot less developed from this. And I learned a lot just by looking at their puzzlement of what I was saying, and then after that I really realized what are the things, and so things are much better shaped right now because of them. So thank you for watching the presentation. I hope you found it interesting, and again, if you have some ideas that could be of help to make this project go forward, do let me know. I'll put in the description some more pointers to things that I've been doing. Thanks.